Hello, everyone. Can you hear me? Okay. Please turn on your camera so that I can see you. Okay. Thanks for coming for today's lecture. Today, we'll finish our discussion about the training the neural networks, the practical issues, and we're going to see some actual examples, case study of convolutional neural networks that we learned previously. So before we start, I have some announcements. So this afternoon, I will release the score for your proposer. And I already selected 16 proposers and 4 additional conditionally accepted projects. So you will be notified sometime today. And the grade itself is really great. The average is above like 42. Oh, okay. Yeah, and the median is like 45. So everyone actually got quite nice scores. And about this will be converted to 1/10. So the highest score possible here is 50, but it will be converted to up to 5, and it will be added to your final score. So good job, everyone. I really like a lot of proposals you submitted. And I will send the detailed guidance to match the team members. So yeah, you will receive an email this afternoon from me, and the matching procedure will start. So for the team leaders, you are going to please put your contacts, your phone number, email, or KakaoTalk ID, or whatever. If you prefer, if you don't want to release your phone number, you can skip, for example. But for faster communication, I encourage you to share your contacts in the spreadsheet. Then all other students will be able to see your actual proposal PDF file, and they will choose which project to join. And then what you need to do is you will admit up to 3 members among the applicants. You can actually decline if you don't want to work with the students, but I encourage you to actually accept as much as possible, because you will not have that much chance. If someone applied to you but you decline, then later it's actually have lower chance that you will have another student joining, then someone will be randomly matched. So please talk to them and try to find the best person you can work with. But I don't recommend actually declining someone who is willing to work with you. And for other students who got rejected their proposal, I'm sorry about that. Actually, I do see that we have more great projects, but considering the capacity of our class and the scope and everything else, that is not really related to the quality itself of your proposal, I had to reject some of them just because of the capacity. And probably you will see that you got like full marks, 50 points, but still it was rejected because of just the capacity. So I'm sorry for that. But if your proposal was not accepted, you will need to join other students' proposal. So please try to read the PDFs. You will see the titles and the links to the proposal itself, and you will need to choose one, which is your top favorite projects, and you can apply for that until up to 3 applicants at a time. And the leader will choose to accept or decline. And if someone is declined, then you can apply there. If not, then up to 3 students, then that will be fulfilled. And for those conditionally accepted projects, those projects will be processed only if 3 or more students actually join that project. If not, those conditionally accepted proposal will be canceled, and they will on. Also, the leader will need to join another project. So that's the rule. And we are going to finalize these team matching by this Friday. I didn't specify the exact time here, but according to my last semester's experience, it will be actually done earlier than that, because everybody's looking to join their favorite projects as soon as possible, and that will be finalized actually quite quickly. So keep tuned for my email, and I will need to finalize some of those gradings and some comments, and then I will try to release this evening or this afternoon sometime today. Any question about this? Okay, if you don't have any questions, we can start today's lecture. Yeah, I'm so excited about these proposals. Last semester, we actually had 19 great projects, and everyone actually submitted quite nice paper in the end. And we are already working on 3 papers to submit to the top conferences. So I hope you guys will be doing the same thing. And yeah, let's see. And okay, today we'll have some review questions as usually. So in the last lecture, we learned about how to train the neural networks in practical settings. So let me ask some questions to students. Songhee, Park Songhee, are you here?
Yes.
Okay, can I see your face? You are in the cloud.
Oh.
Yeah, great. What is overfitting?
It's like.
Yeah, I can hear you.
When the model is too fitted to the training set, it is overfitting.
Yeah, that's right. So the model is unnecessarily complex compared to the pattern that we would like to learn from the data. The model will eventually learn even the noise in the data, which we don't want to learn or get trained. So after that, with the overfitted model, that will just perform well on the training data, but not on the evaluation or validation data set. So that's the definition of overfitting. Great job. And as a matter of overfitting, we learned about several different ways to deal with it. And one of them was the L2 regularization and L1 regularization. So I'm going to ask to Yang-su. Are you here?
Yes, Professor.
Yeah. What's the difference between L2 and L1 regularization?
I'm not sure, but L1 is a weight W at the term. Yes.
Okay, why do we do the L2 or L1 regularization? What's the common theme of those before we talk about difference?
We use regularization for penalizing the parameter.
Why? Yeah, that's correct. We actually like to penalize the weights, but why? Okay, it's okay. Let me ask the same question to someone else. Marker, Yuran-sen?
Yes, Professor.
Yes.
I did say Michael.
Oh, sorry. Marker. Yeah, sorry.
Is it me? Can you hear me?
Yeah, actually, both of them are talking together. So let me call you the full name. Jungersen Mads Emil Marker.
Yeah, can you hear me?
Yeah, is it a right pronunciation?
Yeah, that's perfect. Thank you.
Okay. Are you from Sweden?
No, Denmark.
Denmark, I see.
Yeah.
So, yeah, what's the difference between L2 and L1 regularization?
So L1 regularization uses the absolute value of the weights, and the L2 norm uses the norm or length of the squared distance.
So what is the motivation of using L1 instead of L2?
L1 doesn't punish like outliers as much as L2 does. Like extreme outliers.
That might be true. But what I'm asking is, why do we use L1 instead of L2?
Oh, because it's computationally easier to calculate.
Yeah, why is it computationally easier?
Because you don't have to take the square, you just take the absolute value.
Oh. I think you're talking about the hinge loss stuff. Do you remember that we had a circle and the diamond, and we talked about the situation that some optimal point is outside of those circle or diamond, and then it maps to within that area, and then what happens? Why should we use diamond instead of circle?
I'm not really sure why to use the diamond instead of the circle. Maybe you...
Okay, it's okay. So yeah, in the last lecture, we discussed that in probably you may remember some picture that if we use L2, it's a circle. And if we use L1, then that's a diamond shaped. And if the optimal parameters of theta 1 and theta 2 and so on are outside of that shape, then regularizing those parameters actually means that they need to be located within that shape. And if we use diamond, then it encourages the sparsity. Many of those values will be mapped to 0. That's the key points. So you can just remember that. If we use L1, it promotes sparsity. So our model will be sparser than using L2. In other words, if we use L2, those weight values are penalized equally wherever they are located. But if you use L1, then depending on where they are located, if that will be mapped to 0, some of those values will be mapped to 0 if they are not really, really necessary. So yeah, that's the main difference. And please keep remembering this. This is really important thing. And let me ask another question to our data science students. Uni. Yeah, we learned about dropout. So can you explain what it is and how does it work?
So in MLP, there are a lot of weight nodes over each layers, and we want some of them not like performed towards the next layer.
Sorry, I don't understand. Can you paraphrase it?
So we don't use the whole of weight nodes during learning process. By setting some of them as zeros rather than their original values. Is it right?
Yeah. Why do we do that?
To prevent overfitting.
Yeah. Okay. Okay. Yeah, it's partially correct. Let me ask to another one. Yurim? 최유림?
Yes.
Yes. Why do we use dropout?
Java forces the model to Java forces the model to learn from various clues.
I can't hear you clearly. Oh, sorry.
Can you hear me? Can you
Yeah.
hear me?
Can you take your mic closer? Sorry.
Can you hear me?
Yeah.
Yes. Java forces the model to learn from various
Various
clues.
clues. Yes, that's correct. Yeah. So dropout was disabling some of those edges randomly while we are training, and which means the top nodes is getting the clues from different aspects, and each of those are represented by the different nodes below that layer. And from there, by disabling some of them, we are kind of requiring the model to rely on different vectors or clues to classify the image to be something like cat. So we have shown that some examples with the cat, and some of them, some node is in charge of its eye, some of them ear, and so on. So by disabling some of them, we are kind of requiring the model to still learn to classify based on some partial clues of that, so that the model can classify each classes more robustly. So that's the main idea of the dropout. Great. And lastly, I have one more question. Let's ask another data science student. 경선? 경선?
Yes, Professor.
Yeah. Can you tell me more about momentum? What is it and why do we use it?
Sorry, Professor, I cannot explain this in English.
Okay, you can speak in Korean then.
Thank you. 모멘텀은 그 그레디언트 디센트를 할 때 그 기존에 가던 방향을 조금 더 그 물리학에서 말하는 관성처럼 조금 더 그 방향으로 조금 더 가중치를 두기 위해서 모멘텀을 주면은 조금 더 옵티멀 포인트를 더 잘 찾을 수 있다는 데서 착안한 거에서 모멘텀을 사용합니다.
Yeah. Okay. Yeah. He explained in Korean quite well. So let me translate. So what is momentum? It's more like an inertia in physics, unlike its actual name. So when we use the gradient descent, we keep storing the historical gradients, and we use that as kind of accelerating the movement towards that direction. So if it was kind of moving to the same direction for a long time, then we accumulate those gradients, and actually we can go further than the gradient that we are calculating at this moment. Why do we do that? We can use that for not stucking at the saddle point, because at the saddle point, some of those gradients will be zero and it will be stuck there forever. But if we have some accumulated positive or negative gradients for that particular direction, that we can still get out of that saddle point. So it actually also helps to converge faster, and we can get out of this saddle points and local minimum and so on. So that's why we are using momentum, and we have learned various methods to using momentum, like AdaGrad or RMS prop or Adams. So please review these materials if you are not understanding what I'm talking about. And I'm kind of warning, after lecture 9, actually starting at lecture 9 and later, all the materials will be much, much more difficult than what we are currently talking about. So please review these materials. If you are not following these, then that will be much harder So great. Let's talk about today's discussion. So we are still talking about how to train neural network, especially in a deep setting. And we are finishing this discussion with this learning rate scheduling and the batch normalization today. So all the optimizers we have learned, the stochastic gradient descent and its improved versions like AdaGrad, RMSProb, or ADAM, all optimizers actually we need to specify the learning rates. All of these are based on the gradients computation, and using that gradient, we update the parameters using some kind of gradient descent-like algorithms. So how much we move it at each step, that is determined by the learning rate, and this is super, super important in machine learning. You need to play with different learning rates and learning rate scheduling and all the things to make your model actually to work. Otherwise, even though you have perfect model and perfect data set, still it will not learn as much as you expect. So here's the good picture that the effect of different learning rates. What we'd like to do is something like this red line. With proper learning rates, the loss will start here and it will decrease like that. And at the end, it will converge to some value, and it doesn't overfit here. So this is the right, perfect, proper learning rate schedule. If we use lower value than that, then what will happen? We compute the gradients and we move towards that direction, but smaller than we need to. So it's just slow. We just converge to the same points, but it would basically take longer time, right? So with lower learning rates, it will eventually converge to some points, to the points that we would like to go, but it just takes longer time. And here, the longer time means not just a few seconds or a few minutes, but it will take a few days or weeks. So yeah, you will need to train your model as soon as possible to make some impacts in your company later. But if you use a wrong learning rate, that means your project will take several months longer, then your boss will not like it. Even more serious problem will happen if you use too high learning rates. It will be converging, it looks like converging faster at the beginning, but after that, it will need to converge to some points, close to the local minimum. But in that area, it cannot find the fine-tuned optimum points, but it will just jump too far away around that local optimum. So it will be not converging like that, and it will converge actually to the worst points, which is actually bad. So the eventual performance will be actually worse than using these proper learning rates. And if we use even higher learning rates, then what will happen? It will not converge. It might diverge like that. So if you observe some situation like this, then you have to suspect that your learning rate might be too high, and you can start with a smaller number. So, and I will talk more about this, but usually we schedule the learning rate. Previously, with shallow neural networks, we were using just constant learning rate. But these days, it's common to start with some large initial learning rate and then decay it over time, something like this. So learning rate, you start with some value, and then at some fixed point, you reduce it by some ratio you decide. So for example, here, this is actually the actual example I used when I was training some video models at Google. So initial learning rate was this, 1e minus 4 here. So until the half of the training, we use this learning rate. And then at the half, we reduce it to 1/10 multiplied by 0.1. So it becomes 1e minus 5. And we run for about quarter of the entire epochs. And then we reduce it again 1/10. So it becomes 1 to the e minus 6. So that looks like quite arbitrary, but actually that practically works really well. So why do we do this? right after reducing the learning rate, we often observe some further improvement, which otherwise may not happen, which this figure actually shows. The performance or loss actually gets better up to this point, but at this exact point, we have reduced this learning rate to 1/10. And we see that the loss actually drops quickly. Otherwise, it will just very slowly converge actually above this. But with this learning rate decay, we actually observe that the loss actually dropped significantly at that point. If we don't do this, actually, it will not happen. And does it actually matter? Yes, we compute this accuracy. We also see that the accuracy gets significantly better at that right point. From 10 to the minus 5 to 10 to the minus 6, it's negligible, unfortunately, but sometimes it also helps. Or instead of this step, you can actually use some functions like this to gradually reduce these learning rates, starting from the cosine functions or like linear scheduling or inverse square roots. So the rule of thumb is you have to start with some large value at the beginning, and then gradually it needs to be reduced, because otherwise, in the end, it will not converge to around the local optimum. So that's the common strategy. And usually I just told you that we start with some large value, but at the very, very beginning, it's not a good strategy to apply that large learning rate right away to just warm up. So because we start at some random points, there we don't know what it is. That can be just some saddle point, or it may be some, I don't know, it's landscape. We don't know anything about that. So we just start with initial warming up, and starting from the 0, we increase the learning rate linearly up to like 10% of the entire epochs. And then we apply this highest learning rate at the beginning until some points, something like that. So yeah, you may see that these are probably, it looks like some arbitrary strategies, but the just main theme is you start with some large learning rate and you need to decay it, and then you will probably see improvements of your eventual performance. So play with different strategies and different values in your actual data, and you need to find the best combinations that works for your particular problem, especially for your project. Okay. And as the last topic, we are going to talk about the batch normalization. So in the last lecture, we talked about data preprocessing, and we talked about some strategies to make the data set to zero-centered and normalize. Why? Having the zero-centered univariance data is beneficial in multiple aspects, as we talked about in lecture 6 before. But for the very first layer, we can just make it by changing the data set. But what about the next layers, in the intermediate layers? It's harder to actually change or control those values because it's the output of our model or our layers, and we cannot arbitrarily change that, right? So they may not be zero-centered or unit variance. It can be just arbitrary outputs. So how can we enforce them to be zero-centered or unit variance? So the answer is quite simple, according to the batch normalization paper. Do you want zero mean unit variance activations? Then just make them so. How? What is the normalization in statistics? Given some values, we subtract its expectation or average empirically and divide by its standard deviation. So for all the inputs, if we know these values, then we can normalize them. But if we have very large scale data, then computing it is actually not as efficient as we expect. So what you can do is, we usually do that in mini batch setting. When you update the with the gradient descents like algorithms, then you have the mini batches, and you can actually compute these expectations and standard deviation among the examples in the mini batch. So suppose this is the batch you have, the mini batch you have. You have n examples, and each of those has d-dimensional vectors. And within this mini batch, you compute their mean and their variance, or standard deviation, taking square roots. So the mu j is the mean of the examples. You have n examples. I is the index for them, and you compute their empirical mean and storing it as mu j. And according to this definition of the standard deviation, you can also compute this sigma j square. And then you would normalize the xij by subtracting the mean and divide by standard deviation. It might be the case that the standard deviation is very, very small number. So you just add some epsilon to make it a little bit more robust. So here's a question. What is the dimensionality of these mu, sigma square, and x hat? 성현? 박성현?
Yes.
Yeah, what's the dimensionality of these?
Dimensionality of mu is d, and
Yep.
sigma is d also, and x hat is n by d.
Yes, right. So it's a good practice to always check the dimensionality of each variable to understand algorithms or anything we learn in this course and in machine learning in general. So here, the mu is average of all the data points in the mini batch. So n should not be there. So it's just d-dimensional vector. Same thing for the variance or standard deviation. And x hat should be in the same shape as x, because we just normalized the values, but its shape should be the same. Okay, great. So then we have the normalized values after our computation in each layer. And before we forward it to the activation function, remember that why do we do this normalization? Zero mean and unit variance data is beneficial when we compute the gradients. So before the activation function, we would like to make it zero mean. And after that, after we apply the activation function, and we will have better shaped gradients if they are zero mean. So that's why we are doing this. So before we forward it to the activation function, we normalize these values. But here's the problem. What is the neural networks doing? We train those models and fit those parameter values to connect the input vector x to some label y. And all of these values are fitted by the backpropagation methods to best estimate the expected outcome, the label score for each y, right? So if we arbitrarily change the value using these normalization techniques during these layers, then the next layer will receive some different values than it's expected, what it's expecting, right? So there need to be some additional stuff to compensating. So we just change the values to zero mean and unit variance just for our convenience. But after we taking the activation function and compute the gradients, we need to get it back to its actual values. So that's the point here. So to address that, we need to have the reverse transformation to make it as a kind of identity function. So given the input values xk, we normalize them to x hat k by subtracting its mean in the mini batch and divided by its standard deviation. Then we have to multiply back the standard deviation and add these some value to compensate for this expectation we have subtracted before. So these two additional hyperparameter, this two additional parameters called gamma and beta. These are learned from the data, so and they will be added and stored in the batch normalization layer to compensate this arbitrary change. So to summarize, what do we do in this batch normalization? Given a mini batch of the data set, we compute its average and standard deviation. And using them, we normalize the input values and use those normalized values to compute the gradients before we move on to the activation function. But after that, we need to get it back by multiplying back these gamma and add these beta to compensate for these adjustments. So these values are learned from the data, and they will be used in the batch normalization layer. That's it. That's just a summary of this batch norm. It's super simple thing, but it looks scary because it has some math, and why should we have this normalization and we get it back? But that's it. That's just the essence of the batch norm. So at the training time, we have mini batches. So we are using its distributions to make it unit variance. But what about at testing? At testing, we may or may not have mini batches. So we are not usually relying on the mini batches at the test time. So we just keep the running average of these mu and sigma squares when we train, and then use those values at testing. So during testing, this batch norm becomes just a linear operator because we just multiply something and, subtract something and divide by something and multiply that same value and add the same value again. So it's just a linear operator at testing. Here, the main assumption is that the training data is IID, or independent and identically distributed. We learned it before. So otherwise, these mu and sigma square will not be very similar for mini batch by mini batch, which doesn't make sense to apply this kind of things. So that's just main assumption that we have the IID distributed data points, and for each mini batch, given that the mini batch is not too small, we have very similar mu and sigma square, even though we process multiple mini batches. So why do we use this? Actually, it helps in multiple aspects, and it's great. Just use it by default. So it makes the deep networks much easier to train because it moves to zero mean, and the gradients will not decay as much as it does without this. And actually, it helps the gradient flow for that reason. And we can use higher learning rates because the gradient is more robust, and it converges faster. So every good thing happens when we apply this batch norm. So, and also the networks become more robust to initialization. We can start from any values more robustly, and acts as a regularization during training, and also minimal overhead at test time. It's just one layer, just computing the mean and standard deviation and just subtracting and division. So it's very simple. So no reason to not use it if the data set is IID. That's the important part. Why not batch norm? We should not use batch norm if that's not the case. Batch norm is conducted on mini batch at training, as I told you, while overall training data at testing. So if the training data distribution is significantly different from the testing data points, it might be the case in practice. Usually, if you train a model in experimental settings at the lab or for some public data sets, the IID assumption holds usually. But if you, for example, trained a model 2 years ago and launched it on some commercial system, and you just use that model for 2 years, the distribution of the user behavior will be the same today compared to the 2 years before. Maybe or maybe not, right? There will be more items or more new services and new users. And if you launch the same system in different countries, user distribution will be completely different. Everything will change. So in reality, this IID assumption may not hold, especially if you use that system for a long time. So if the training data is not IID, then what should you do? So the same author of this batch norm paper actually published another paper after that, which is called batch renormalization. So if you have training data and testing data with different distributions, you can actually compensate that difference by using some additional renormalization. So if you're interested in, you can read this paper to understand what they do. Okay, so how do you use batch norm in practice? You just understand how it works theoretically in today's lecture. Then using it is super simple. The batch normalization is already implemented in TensorFlow or PyTorch. you can just add this additional layer between convolution or fully connected layers, and then before you actually take the activation function like ReLU. So just you can call this layers.batch normalization with some hyperparameters and feed this data. Then you just store it to the same variable and feed it to the activation function. So it's common to insert the batch num after the fully connected or conv layer before activation function for that reason. And after that, this batch num succeeds a lot, and then a lot of people did similar research. So layer normalization, instant normalization, or group normalization, a lot of new normalization techniques are proposed, and you can actually compare with this cube. So in the batch norm, we have this h and w is the height and width. So it's to this dimension, these are different pixels or the values in the tensor. And C is the number of channels. N is the different data points. So the number of data points in the mini batch. So in the batch norm, we take the average and standard deviation across different examples in the mini batch. But we can do that the same thing in the same layer across the channels, or across the instance, actually the pixel values. So there can be multiple different ways of doing this normalizations. Actually, so group norm is something like this. We use a subset of channels, not a single or not the or, but you just group them. Usually, if you use these kind of things, these three actually have some physical meaning or some intuitive relationship between them. So you can use those prior knowledge to normalize these values. So if you're interested in, I encourage you to read these papers. And actually, layer norm is very, very widely used these days. Instant normalization is as well. So I encourage you to read these papers and understand what's going on there. The basic philosophy is very similar to batch norm we talked today. So far, so good. And this is the end of lecture 7. And let me stop the recording here. And if you have any questions, you can ask it now.